Hello, everyone. I guess the first thing I would like to do is apologize because I haven't been uploading any physics content lately. The reason for this is because I've been really busy with my research and starting off my PhD, and I haven't had much time to actually make any content. But now I'm at the stage of my research where the only thing I can do is wait for my code to run. So I guess now I do have some spare time. So I decided to do this lecture. Well, it's a continuation of the black hole lecture, but it's because I read something interesting on wormholes and multi-black hole solutions, and I decided to talk about how the Schwarzschild geometry can yield wormhole and multi-black hole solutions. So let's go. First, let me outline what I'm going to talk about in this lecture. So I'm going to summarize what we did in the last lecture, which was a long time ago. I think it was titled Particle Motion in Schwarzschild Geometry. So you better look if you forgot what we did in the last lecture, you better go look at that. Then next we're going to talk about, well, we're going to mathematically describe wormholes and multi-black hole solutions. So we're going to first define what a wormhole is. Then we're going to talk about conformal flatness of the Schwarzschild geometry. Then we're going to talk about how we yield asymptotically flat regions using diffeomorphisms. And finally, we're going to talk about how we obtain multi-black hole solutions from the Yamabe equation. So let us summarize what we did in the last lecture. So in the last lecture, we described the motion of both non-relativistic massive particles and massless particles along geodesics in the Schwarzschild geometry. So using the Lagrangian formalism, we derived the equations of motion. And subsequently, we calculated the capture cross-section of the massless particle and the non-relativistic massive particle near a black hole of mass big M. The capture cross-section of a massless particle is as follows. And the capture cross-section of a non-relativistic massive particle is this, where v is the velocity of the massive particle at r to infinity. Now I guess we can talk about the objective of this lecture. So the objective of this lecture is to mathematically describe both wormholes and multi-black hole solutions. In order to do so, let us mathematically define what a wormhole is. A wormhole, or a Einstein-Rosen bridge, has to have three properties. So the first property is, suppose that it is this the surface is described by a hypersurface sigma of a spacetime manifold M and M. For a wormhole to exist, sigma has to have a non-trivial topology. And additionally, it has to have a minimal areal radius, where r is equal to m over 2, where m is the mass and r is the radius. So this is known as the throat of the wormhole. Finally, the throat of the wormhole has to be formed by the intersection of two black hole horizons with the hypersurface sigma. That was the mathematical definition. Now, for those who are more physically minded or more geometrically minded, we can just look at this picture. So we can see that this, so basically, this wormhole is formed by the intersection of two horizons of a black hole. And we can see that this throat here has a set radius, so it's quite constant along the throat. So this areal radius has to be m over 2. But what is more interesting is that a wormhole actually has two space-like separated regions. And these two space-like separated regions are asymptotically flat. So you can see here and here. So this diagram is called an embedding diagram. Now we can talk about conformal flatness of the Schwarzschild geometry. So recall that spacetimes with a non-rotating black hole are described by the Schwarzschild metric. So how the Schwarzschild metric is derived is what we do is we solve the vacuum Einstein field equations, assuming spherical symmetry. And doing so, we arrive at something called Birkhoff's theorem. So basically, spherically symmetric solutions to the vacuum Einstein field equation are static and asymptotically flat. And to get the Schwarzschild metric, we have to use a boundary condition called the weak field limit. And if you don't remember this, you can just go look back at lecture 1. I think it's called Birkhoff's theorem. Yeah. So the wormhole solution, I guess in this form we can see, is not so obvious because we can actually, look at the previous diagram. There are two asymptotically flat regions, one up here and one down here. But in this equation, we can only see one, so namely as we set r to infinity. But the whole point of relativity is that we can always make coordinate transformations. Because relativity is observer relative. So to see it, we need to make the Schwarzschild metric spatially conformally flat. So that is, we need to write the Schwarzschild metric in the following form, whereas capital psi and capital phi are functions of a new radial coordinate rho. So notice from the previous equation here, right? Theta and phi are left invariant, so they remain the same. So therefore, we just compare the d theta squared term and the d theta squared term here. So basically, this r squared term has to be equal to rho squared multiplied by capital phi squared. So we get this first equation. So by virtue, r is equal to capital phi times rho. That's okay. And similarly, we can compare the dr squared term. So this one and this one, right? So, sorry, by doing so, we get this equation. And this equation seems, I guess, somewhat difficult to solve, but what we can do is we can actually eliminate phi first. So the strategy is to first eliminate phi and then solve for r in terms of rho, and then just substitute. So basically, once we have r in terms of rho, we can write phi in terms of rho. So to solve this equation, we just take 3.4 divided by 3.3, and then we get, I guess, a differential equation. But this differential equation, this first order differential equation is quite nice because it is separable. So if we divide this by this, so 3.4 by 3.3, we get this and this. So by separable, it means that we can separate the variables and we can just integrate to solve. So these integrals, I guess, are not too hard to do. This one's easy. It's just natural log of rho. This one, I guess, is a little bit tricky, but you can, I mean, you can always use Mathematica or Wolfram Alpha, but the strategy to solve this integral is just to set r minus 2m is equal to some, well, you just use substitution, just use u. And then I think you might have to do another substitution in order to get some kind of to basically simplify this side. I think this side you either get some arctan function or some natural log function. So I presume you get a natural log function because what happens is if you get natural log here, you get natural log here, you exponentiate both sides. And you can see here, there's no strange function. So I presume that both sides have to have a natural log somewhere. So now we can solve from r in terms of rho. So this is r in terms of rho. And substituting equation 3.6 back into equation 3.3. So if we substitute r here, we can see that phi is equal to 1 plus m over 2 rho all squared, which is quite nice. So this is quite a nice expression. Similarly, we can do the same with capital psi and compare the dt squared coefficients. And doing so, it is apparent that capital phi as a function of rho is simply 1 minus m over 2 rho over 1 plus m over 2 rho. So this is another relatively nice function. So therefore, we can write the Schwarzschild metric in terms of this new radial coordinate rho. And by doing so, this is called the isotropic coordinates. And I guess to see the wormhole solution, right, we actually can just ignore this dt squared term and look at the first fundamental form. That is, we only look at the spatial parts. So we only look at this term. And we can see here, it is still it's still not apparent that there is two asymptotically flat regions. So if you set rho to infinity, you only see one asymptotically flat region, right? But notice that here, rho equals 0 is a singularity, but it is a coordinate singularity and can be removed if we make a diffeomorphism, namely this one or this one. So by making this diffeomorphism, we find that not the new fundamental form, the original first fundamental form in terms of rho bar can be written as follows. And we can see that this inversion transformation transforms the metric. So look at the form of this metric and look at the form of this metric. They are actually exactly the same, but we just change rho to rho bar, right? So this kind of transformation is called a discrete isometry. And from equation 4.1, it is obvious, so 4.1 here, it is obvious that if we set rho to infinity, then we get an asymptotically flat region. But what is also obvious is that if we set rho bar to infinity, we get another asymptotically flat region. So since rho to 0 maps to rho bar to infinity, and rho to 0 is infinite of an asymptotically flat region, therefore the first fundamental form, H, has two asymptotically flat regions, and thus this must yield a wormhole solution. So I think this is quite beautiful. But from the previous slide, we can see that the Schwarzschild metric can yield wormhole solutions, which is already quite interesting, as just making a coordinate transformation, we can see the wormhole solution. However, I believe what is even more interesting is that the Schwarzschild geometry can also yield multi-black hole solutions. To see this, we need to introduce the equation, the Yamabe equation. So, however, before we do so, we need to write the Einstein equations in a different form. For mathematicians, the Einstein equation, the equation we need is the Einstein equation written in terms of the first and second fundamental forms. For physicists, these equations are called the Hamiltonian and the momentum constraint. And the derivation for these equations is quite involved, and I will probably do it in another video because it will take up a lot of time to do. And I guess it's not super important in this case. We just need to know what they are. So, but here, let us just take these equations for granted. So what are the Hamiltonian and momentum constraints? So the Hamiltonian constraint is as follows. So basically it's this one. So R superscript 3 plus k squared is minus kij times k superscript ij is equal to 16 pi rho. So what does this mean? Kij is the second fundamental form. K is simply the trace of the second fundamental form. And R is the Ricci tensor on the hypersurface of the first fundamental form, hij. And moreover, rho is simply the 0,0 component of this energy momentum tensor. The momentum constraint, on the other hand, is as follows. Well, it's a very similar equation, but here, this is called the spatial covariant derivative. So basically it's, I guess you can think of it as the covariant derivative projected on hij, so projected on the first fundamental form. And Sj is simply the 0j component of the Tij, which is the energy momentum tensor. So since the Schwarzschild geometry considers vacuum solutions, the energy momentum tensor is 0. Therefore, rho is 0 and Sj is 0. I mean, that's pretty obvious. Now, recall that if there are two metrics, hij and h bar ij, they are conformally related if they are related by some conformal factor. I'm going to call this var theta. So var theta here is the conformal factor. So now what we can do is we can calculate the Christoffel symbols on the hypersurface sigma. So this is just done by, I guess we can say, ignoring the time-dependent component and just compute the first fundamental form. So it's basically very similar to, so the Christoffel symbol here is similar to the normal Christoffel symbol, but we just replace gij with hij. So we replace the metric with the first fundamental form. So we can write this in terms of h bar ij and var theta, which yields this. We can see here that we have a bar gamma, so we have a Christoffel symbol bar. So this Christoffel symbol bar is basically the same Christoffel symbol, but we just replace h with h bar. And we can see that we have a lot of Dirac delta, is not Dirac delta, sorry, Kronecker delta functions. And we have some natural log of the var theta component. So this equation is, well, if we compute the Ricci tensor later, it would be quite ugly. But so after lengthy calculation, we know that the Ricci tensor of h. So this, as I mentioned before, is the Ricci tensor of hij. So it is the Ricci tensor projected onto the first fundamental form. So this is equivalent to basically the Ricci tensor bar minus this really ugly function of theta and the first fundamental form. So here, this bar covariant derivative and this bar Rij are the spatial covariant derivative and the Ricci tensor of H bar Ij. So, but I guess we don't actually need this entire form because, as we can see before, the Hamiltonian constraint only concerns ourselves with the Ricci scalar, So what we can do is take the trace and we get this. So this equation drastically simplifies, which is quite nice, I guess. But recall, the Schwarzschild metric is time symmetric. And this means that the initial data must also be time symmetric. So what does it mean for something to be time symmetric? So time symmetry implies that the solution to the Einstein equation is invariant under time inversion. So if we set t to t minus t, it should be the same. I mean, this is quite obvious because in the Schwarzschild metric, there's a dt squared term. So if we replace it with minus t, so minus t squared is also t squared. So it wouldn't change the Schwarzschild metric. So to do this, I guess, but the problem is we need to translate this into the new Einstein equations with the first fundamental form. So how do we do this? So to do so, we can simply make Hij time independent, and thus the partial derivative of Hij just is simply 0 on the hypersurface sigma. But what does this imply? This implies that the second fundamental form is also 0 on the hypersurface sigma. Thus, the Hamiltonian constraint simply reduces to R is equal to 0. And from here, if we see that if R equals to 0, we get a nicer equation. So we get, by doing so, we just setting the right-hand side of equation 5.6 to 0, we get the Yamabe equation. So this is the Yamabe equation. And there are many interesting properties of the Yamabe equation. Firstly, the Yamabe equation is an elliptic equation, as this operator here is simply the Laplace operator. So therefore, there exists a unique solution to the Yamabe equation on sigma given appropriate boundary conditions. Now, recall that to obtain the wormhole solution, we need to make the Schwarzschild metric spatially conformally flat. So here we need to do something similar. However, we need to write this in the context of the first fundamental form. For a metric to be conformally flat, we just simply set H bar Ij to delta Ij. An interesting property of Riemannian manifolds is that conformal flatness can be locally characterized by something called the Cotton-York tensor. So this is the Cotton-York tensor. And if this Cotton-York tensor vanishes, then the Riemannian manifold is conformally flat, which is quite a nice property. Therefore, it is not hard to show that R bar is also 0 for a conformally flat metric. And thus, the Yamabe equation reduces to the Laplace equation, which is very nice because we can see that the original equation here is highly nonlinear because these two equations have nonlinear terms. Even this one, it is also nonlinear. So even the Yamabe equation is nonlinear because R bar contains a lot of nonlinear terms in theta. But we can see now that by making the metric spatially conformally flat, we get a linear equation. And this is quite important because when we calculate, for example, in the wormhole case, we did calculate the conformal factor. And here theta is simply 1 plus m over 2 rho. But now recall that I said the Laplace equation is linear. This is quite a nice property because we can use the method of images to superpose multiple black holes over each other. So thus, we can write theta is equal to the sum of 1 plus m sub I over 2 rho sub I, where rho sub I is equal to x sub I minus x bar, where x sub I denotes the position of the black hole with masses mi. So this solution is called the Brill-Lindquist solution. And I guess this is going outside the scope of this lecture, but the reason why it works physically is because of something called unbroken local supersymmetry. And this is the simplest example of what are known as supersymmetric brane solutions, which is something that you learn in supergravity and string theory. But that's outside the scope of this lecture. But what is more interesting is the I guess the multi-black hole solution can yield two types of data. So first is the Brill-Lindquist data. So basically what happens is you can have multiple black holes. So in this case, we only have two. So these two black holes, but they only share one asymptotically flat region. So these two, so they only share this one asymptotically flat region. And this figure I did not draw by myself. I got it from the book Numerical Relativity, solving Einstein's equation on the computer. So yeah. And similar, there is another type of data called the Misner data, where they share two asymptotically flat regions. And yeah, I guess this is quite interesting because both, I believe that this is quite beautiful because what we can do is we can, by making the Schwarzschild metric spatially conformally flat, we actually make the Einstein equation linear. So it's just the Laplace equation, which is very similar to what, not similar to what we do in electromagnetism, but in electromagnetism, what we can do is the reason why we can superpose charges to get the potential or the electric field and etc. is because the equations are linear. But in general relativity, the Einstein equation is highly nonlinear. But what is surprising is when we make it spatially conformally flat, it becomes linear. So I personally think that this is quite beautiful and it's quite an interesting property of the Einstein equations. And I guess that's all I have to say. And I thought that this is a very interesting lecture. And I hope you learned something from it. And I guess I'll see you in the next video. Thank you.